So, good afternoon, everyone. So, the next presenter we have is Mbemba Ngum. So, he's an experienced agro-methodologist with over 6 years of experience, and he currently works at the Department of Water Resources as a meteorology research analyst, right? So, in his department, he leads the preparation of agro-meteorological bulletin, weather map, and climate report to support the decision making and climate resilience. He has a master's degree in agro-methodologist engineering in Niger. He also holds a bachelor's degree in economics and management at the University of the Gambia. So he has a background in both teaching and sciences. So this, based on his background, he also did a teaching in geography and agricultural sciences. So which brings a well-rounded perspective of his background in climate change.
He's a consultant. Yeah. For the presentation outline for this project, I will start by going briefly on the introductions, then later the first question, which is the national and the local assessment of the mangroves. Later we will dive into the physical processes behind the optical remote sensing. Maybe even though we are going to just glimpse on the thermal remote sensing method is also very important, like we've seen in the Landsat method. And also we will look at the image comparison in Google Earth Engine. So, and some of the technicalities that we have been able to do. We also look at the supervised classification and SEPAL just briefly. Now, for the introductory part is we utilize Landsat imagery and also the Shuttle Radar for tropical mapping a lot, and it's important to capture it here to know some of the things it does. We look at the Global Mangrove Watch platform, reference layers, and different layers, and how it is applicable to the Gambia and what we want to achieve. So the analysis conducted on the Google Earth Engine platform, which will be very interesting to see, and also some concepts like random forest algorithms and how it is used on forest mapping. We also look at the different spectral indices like NDVI and others. Now for the first part is on the mangrove extent in the country. We've seen that in 2020 we have a mangrove habitat of 609 kilometers square in 2020, so which also has a coastline representation. So the coastline representation, like you've seen here, is 1,064 kilometers. And the non-mangrove sites also are there captured in the graph. Now for the net change, with time series, sometimes you have a gain relatively, and sometimes a loss. We've seen that, for example, in 2016, there was a decline in mangrove coverage in the country. Yes, and some of these areas are noted there, like some is in the Greater Banjul area, like the Tambi wetland, which we are able to capture there, and also around the LRR, not RR, from the OMVG projects that some of us have presented. So some of them are gains we've experienced in the mangrove extent, and also we've experienced some losses. So these are areas that we've experienced gains, and those are the losses sites. And most of the losses are based on erosion, which is the main driver for mangrove loss in the country. Now for the alerts, like during this particular time, like from February around April, there was a significant alert in mangrove in the country, and some of those sites are there captured. We've concentrated on two sites. One is around the Banjul, Greater Banjul area, and also the other one, like a transition between the LRR and also the North Bank region. So some of those alerts, when zoom into them, we found out that, for example, the one in the LRR and this North Bank transition is the OMVG project that is clearly demonstrated when we look at the planet. So for the mangrove canopy height in the country, yes, sometimes, because we've all know that there is a relationship, a very good relationship, and later we'll be demonstrating that here, between the canopy height and also the mangrove height and also the canopy. So here is the mangrove canopy height in the country. So it's around, you have the tallest mangroves around 10 to 15 meters, which are these thicker areas on the graph. So some sites are restorable, like from here, when talking about the damage and the destruction on the threats, the disturbance on the mangrove sites. So with the destructions, whether they are reparable, that is, whether they are recoverable, some of them are not. For example, when zoom into one of the disturbances around Banjul area, you see that there is a construction there, which is like an area of no return. So the construction is already there, so we cannot recover the mangroves again. So some sites which are restorable are like 532, based on the analysis in the Global Mangrove Watch, and like most of for the restoration, when we are talking about whether there is a success that we will be achieving if we are to embark on any restorable practice, so we still have a chance of around 70% of succeeding in that adventure. So for the disturbance, the fisheries pressure disturbances, we have two notable areas I was able to highlight. So around the Tanji area and also the Carton area. Why? Because these are very large artisan fisheries sites with foreign vessels, and there is a pressure in these areas. So it's very important to see that Global Mangrove Watch actually has a platform which can help us stay alert and also issue early warning on certain dangers, especially on mangroves and on fisheries in the country. So for the second part, which is the physical processes behind the remote sensing, so to explain it in a nutshell, remote sensing is a very widely used terminology now, but we just need to have certain concepts, like the radiation, which from the sun, the optical radiation, which shines and reflects light, where now there is a sensor somewhere in the satellite which captures it. That is when it is optical. Now for the radar remote sensing, which it uses its electromagnetic waves and also recaptured them to do and be used for different applications. Now, to understand why plants are green is you have to understand the optical remote sensing method and how it shines on the leaves and also what is reflected back. So given our nature as humans, we can only see in the visible. This is why the only light that comes out of the chlorophyll is the green from the sun. So this is why we are able to perceive plants as green. So let's have a look at some certain processes we are able to actualize with the supervised image classification. Now we've captured two regions. One of them is the central badibu. We are able to view the layers. So this one is the Mangrove Watch layer, the Mangrove Extent that we have done with the random forest method, and this one is a combined layer. So in the platform, in the API system with the Jupyter Notebook, this we can capture it. So now the mangrove area comparison is like 74 and the 42 from the Global Mangrove Watch, and also what we are able to, from our data that is used from the random sampling method. So this one will be actually very long to explain, but what we need to understand is the spectral indices. First, we have to do a cloud computing if you are doing a supervised classification. So the cloud computing will help you choose the clouds that are contaminated to remove them, and also give you a good classification, because like clouds are like hindrance from where the sensor can see. So now when that is done, actually there are techniques like the QA pixel method, that is you use the quality access to remove the clouds, and based on the cloud, if it is a CI cloud or if it is a convective cloud, you have to remove it. So the other thing is the spectral index. So the spectral index, what we need to understand there is we use certain indexes from this random forest method, which is like a decision tree to choose most of the important indexes. Like now we look from the Shuttle Radar Topographic Mission, was used more to classify the area where we have mangroves and the area where we don't have them. So now for the sample distribution, when we data set after the random forest method, we are able to use a total of 7 samples. We use 6 for the data set and then later 1 for testing. Now this is the summary in a tabular form. So now for the canopy height in the platform, this is when we only visualize the height. Here we can visualize the above ground biomass, and this is just the extent if it is visualized in the platform. Now all of them now, if you click on any part, it will give you the longitude and latitude, and also the canopy height, the mangrove extent in that area, and other indexes that are important. So now if you look at this one is done for the region of KMC. So if you take KMC, for example, this is it after you put it in GIS and you spatialize it. So, but if you want to see the mangrove where the height is important, you can easily put it in a hexabin to see the thicker one shows that the mangrove canopy height there is important. And also the relationship, that is for the validation method, there is a good correlation, which is like 0.98 method that confirms that there is a linear relationship between these two, and that is used in the random forest method. So now with the sepal, this is how we did the mosaic images, and these are different bands that we are able to use to do the classification. So we need to have this first before the classification, and finally we can use it to classify the area where we have mangroves and where we don't have mangroves, which is a different method to achieve the same objective that we have done in the art engine, and which can also be done elsewhere. So thank you very much for your kind attention.